So our next speaker is Swarnaditya Hazra, and he is talking about probabilistic plugging of airways by sliding mucus film.
Okay. Hi everyone. So today I'm going to talk about when does the mucus film form plug in our pulmonary airways. Now this question is very relevant in the context of some respiratory distress such as asthma. Okay. So before dive deep into the topics, I'd like to thank my PhD supervisor, Dr. Jason Ryan Picardo, and my institute, IIT Bombay. Now Jason is an associate here and he often tell me that I should visit this place at least once during my PhD tenure, and I am very grateful to ICTS and the conference organizer for giving me this opportunity. Going back to mucus, it is act like a first line of defense in our respiratory system as it covered the inner wall of our airways. Now this inner wall contains cilia and that cilia beats in a synchronized fashion. This beating of cilia ensured the flow of mucus, and on top of that there is oscillatory airflow. So now this mucus film is often subjected to surface tension driven Rayleigh plateau instability. In our everyday life, we frequently encounter this Rayleigh plateau instability whenever we open a tap. Surface tension do not allow the water to flowing in a uniform column, rather it creates some undulations. So in the mucus film, because of Rayleigh plateau instability, most of the mucus start gathered into a liquid bulge, and that liquid bulge, depending on the volume of the mucus, can form plug if the mucus volume is very high. On the other hand, if the mucus volume is not that high, it can remains there as hanging undulates. So this entire thing is an equilibrium based phenomenon. And from the equilibrium calculation, we can easily predict a threshold volume. So greater than that volume, we have plug in the airways, and less than that volume, we have hanging undulates. So moving on, in reality, our airway is quite long. So what will happen there? Is it like that all the mucus gather together and form a big giant hump? The answer is no. Then how many humps will appear? This is very similar to Rayleigh's classic idea. How many drops can appear from an unstable liquid jet? And Rayleigh proposed that there is a fastest growing mode and that pop up a length scale. And this length scale determine the pattern which emerges from the systems. So I make it simple. Let's say we have a airway which has the length of 4 lambda, where the lambda is the length associated to the fastest growing mode. And we choose two different initial conditions. So what will happen? We always ended up with this thing. That means there is always 4 hump. So doesn't matter whatever initial condition you want to choose, unless your domain size is 4 size of lambda, you always ended up with 4 humps. But that's it. Linear analysis can go up to that. It can only predict the number of humps. But when we are going to go deep into the question, that's what happened with the fate of this hump, we are entering into a very dangerous territory, that is the territory of nonlinear dynamics. And for that, we need model, we need simulation and all. So, yeah. So as usual, we start with continuity and the Navier-Stokes equation. Cylindrical coordinate system is a natural choice. We consider mucus as a Newtonian fluid, and we are including the cilia motion as a Couette flow kind of boundary condition. Apart from that, we have our tangential stress and the normal stress at the interface. We observe that we are focusing on the intermediate region of the airway, and there the effect of air is not significant on the dynamics of the mucus. So we consider the mucus film as a passive fluid. So after that, we applied a thin film reduced order model. And finally, we got these scary looking PDs. We solved these PDs, ran some thousands of simulations by using this initial condition. Now, what is this initial condition? It is like we are taking a flat film. On top of that, we are applying a smooth random noise. So what we will get? So let us first discuss one lambda domain. That means the domain is short. There is only space for one hump, and equilibrium criterion is exactly matches. So moving towards the long domain, typically the airway has the domain length of 4 times of lambda. And here we encountered two different types of volume threshold. One, when this each unit cell has the volume of 1.73, remember this 1.73 calculated from the equilibrium calculation. On the other hand, when the full domain volume is 1.73, the first one is named as fastest mode threshold, and the last one we named as full domain threshold. Now let's jump to the conclusion. Before that, depending on the thickness or the volume of the mucus film, we categorized our result into 3 parts. So first, look into the thick film. Now for the thick film, each of these hump cross that equilibrium criteria, that is 1.73, and that's why anyone can form this plug. On the other hand, if we choose a thin film, this is remain open as the volume is far beyond the fastest mode threshold, but still above the full domain threshold. Now there is something interesting going on in the intermediate threshold. Let's say this example. Here we choose the same initial thickness or the same mucus film volume, but with different random realization. Sometimes we got a open case and sometimes we got a closed case. And that leads to the concept of probabilistic plugging. Okay, so now let's look into the full statistical picture of our story. Here we plot the probability of plugging versus the initial film thickness. This red region correspond to the thick film, which are always plugged. This blue region is for the open film. So here the airways is open. In the intermediate region, the interesting thing is going on because there is all the uncertainties of plugging. As we increase the thickness of the mucus film, the chances of plugging become increases. Now why this is happening? Why suddenly one hump becomes so lucky that it start accumulating more mucus than its 1/4 share? To answer this, we have to look into these simulations. So let us look at the first simulation. So these simulations were running with the same initial film thickness, but this is two different random realization. In one case we have intermediate plug, and in another case we have intermediate open. Now if you take a look at the intermediate plug thing, means the top one thing, the hump form, and then this hump becomes lucky and it starts slides. And during this sliding, it starts accumulating more mucus, ultimately form plug. Where in the open case, more or less all the humps slide at a same distance. So this sliding is responsible for the intermediate region of plugging. Now this sliding is a highly nonlinear phenomena as it is a secondary symmetry breaking instability. And because of that, we get this kind of plugging. Now we check our idea. What we did, we measured the distance between the deepest hump from its two adjacent neighbors, and we observed the expected result. For the closed cases, the deepest hump slides more, and for the open cases, more or less, they are slides the same distance. In the next thing, we are checking something, whether there is any role of cilia in this plugging, and we are confirmed that there is no role of cilia in the plugging because we replace cilia with weaker gravity and even we switch off cilia, but the overall statistical story remains the same. So finally, when does the mucus film plug? If we are talking about a short domain, then the entire thing is determined by equilibrium. But when we have a long realistic domain, this thing is governed by the dynamics of the film. Thank you.
We will take few questions.
Thanks for the nice talk. It's known that the properties of mucus depends a lot on the pH level.
We neglect that thing. We did not consider anything because now we are basically focused on a nonlinearity. So we are not looking at the property of mucus. We are considering mucus is like water. So the density, viscosity, and everything is like water because these dynamics is so like if you are considering pH and all, so they don't have any exact role on this plugging kind of phenomena. So there may be some other role. I am not denying.
I would suppose they would play a quite prominent role because even the crosslinks and all, they change
Yeah,
a
that
lot
is important,
depending
that
on
I
the pH.
understand.
So,
But suppose there is one important criteria of mucus which we are not considered here, that is the viscoelasticity. It is the basic property of mucus. Now, on the context of plugging, it is not has any role. But when viscoelasticity is important, because as you all already anticipate that thing, this viscoelasticity thing is a short time scale problem. So when it is from a plug, that is not important. But when it start to reopen, that time scale is a capillary time scale. So at that context, in the reopening context, it is important. So that's why we also omit this kind of other stuff. Yeah, hi.
Did not consider the viscoelastic property of the mucus itself, because if it is moving and the cilia is moving, that's going to exert some shear, I suppose, and change the, I would expect normally a cilia to play a role. That's what happens in our natural systems, isn't it?
Yeah, ma'am, you are correct. So there is one paper recently published in JFM. So they studied the cilia motion and their effect on that viscoelastic mucus, because they considered the Oldroyd-B model and all. So what they find out, unless until we are stick with the healthy airway, means there is some, so the viscoelasticity and the cilia, effect of cilia on viscoelasticity is very much important when you are talking about some cystic fibrosis patient or something like that, where the airway is not healthy. But in the context of healthy airway, these things are not that effective. So we have submitted a previous paper where we considered this. So here we are assuming the cilia motion as a constant fluid flow kind of thing. But in my previous paper, we assumed we put the full cilia model, that full oscillatory cilia model and all. But in the context of like the plugging and all, it is not important. So. Okay, so this is in this model, it is a coarse grain kind of model. So we are not considering cilia density. Rather, we are considering it is like a fluid flow, like this wall is moving. This wall is moving. Yeah, kind of. This is because of Rayleigh-Plateau instability. Rayleigh-Plateau, yeah. Rayleigh-Plateau instability create these unduloids, and cilia just transport these unduloids. So we have not introduced it. So there is some other paper who has introduced it, but it is quite difficult to introduce exact viscoelasticity in the thin film kind of model. So because of the time scale difference. So when you are doing a long wave approximation, so there the time scale is different, but the viscoelasticity time scale is a short time scale. So there is a scaling difference. So that's why what people did in some previous literature, so they use viscoelasticity as a weak effect. But if you want to model viscoelasticity with the full system, so you have to do DNS.